Why should we care about probabilities? I would argue because probabilities are all around us. They shape the likelihood that we buy certain products, that the governments make certain policies, roll out double demerits on holidays, for example, insurance companies deciding how much you should pay to drive a car with insurance or not, whether we win at the casino table, whether we, everyone has probably flipped a coin before, right? So underlying probabilities of flipping a coin are as simple as they get, right? If you flip a coin, you have a 50% chance or a 0.5 chance of getting heads and a 0.5 chance of getting tails if it's a fair coin. This time I got tails, according to this, but you have this probability of 0.5. You have other probabilities all around us for what card you're liking to pick in a casino, or just this picture here is of my kids' beads that they melt into these kind of crazy patterns. But probability is just the study of events in which, or outcomes in which there's just an element of uncertainty that we're not exactly sure what is likely to happen. Why should we care? It's because most of the time, us as politicians are dealing with samples instead of populations. That if we had a defined notion of the population, which is every single card in this deck, then we would be able to have much clearer understanding of what the uncertainties are. Then you have just a sample, some subset of these cards. You have to guess what's here versus what is excluded from it, right? So probabilities are used in political science research because they help tell us whether something is statistically significant or not, and whether they're likely to occur by chance. And the way that I think of it, I showed you in that previous slide, my kids' beads. And so if you think about it, a lot of what we're doing is we're just trying to take a sample from a larger population. So for example, we're measuring let's say, human development, right? And so you look at life expectancy at birth, but we don't actually know people's underlying life expectancy at birth. We have a sample of people that live and a sample of people that die. And so you have some kind of subset of a distribution of people who live and don't live past a certain age. And what we do is we just take these samples and we can take repeated samples. Theoretically, we can put them back or not. And if you do this a number of different times, you'll get an average value of the distribution here. There's only two colors, but you can have a whole bunch of whatever the different number of outcomes is that you have. But theoretically, you take these different samples, and if you take a sample and you analyze it, you're going to get some results. And as long as that sample is random, you're not systematically biasing how you scoop, for example, you make sure that they're well mixed. Then if you take repeated samples, the average value should be roughly equal to what the population is. And so we're trying to decide whether those different values are statistically significantly similar or different from each other, or whether they're likely to occur by chance. So what are the important parts of probability? There's a couple of important ones. All outcomes have a probability ranging from 0 to 1. You have the probability of a heads or a tails coin. There's only two outcomes. Each one has a probability of 0.5. Both of those equal 1. The sum of all possible outcomes have to equal 1. Same with the beads. I have an equal number of black and white beads, so you should theoretically have a probability of getting one color or the other at 0.5. If and only if two outcomes are independent from each other, then the probability of those events both occurring is equal to the product of them individually. So I don't have a die in front of me. I should have gotten one of my kids' board games. But if you roll, let's say you have 6-sided die, so you have 6 potential outcomes. So then each one of those outcomes have a 1 in 6 possibility or of happening. All those 1/6 add up to 1. The probability of rolling a 1 or a 2 is equal to the product of both of those events occurring. Actually, no, that's not right. The probability is of two outcomes like rolling heads twice. The probability of that happening is the product of both. So that would be 0.5 times 0.5. So that'd be a 1 in 4 chance of there being two heads with two flips of the coin, right? What I was really kind of thinking about is the chance of either of the two outcomes happening is the sum of them if they're mutually exclusive. So in the six-sided die example, then the either of rolling a 1 or a 2 would be the sum would be 2/6 or 1/3 chance of both of those things happening. So that was the key difference between them. That if they're independent, the chances of them both occurring is a product. If they're mutually exclusive, then it's a sum of those two different outcomes. If the events are not mutually exclusive, so for example, in the card example, the probability of getting a queen or the probability of getting a clubs, then the probability of getting both A and B, so let's say a queen of clubs, is the sum of the individual probabilities minus the probability of both of those events happening. So the sum of the individual probabilities of getting a queen and the sum of the individual probabilities of getting a club minus the probability of both of those things happening. So those are the basic characteristics of underlying probability. Probability pitfalls. There are a crucial number of assumptions when using probability. They assume it can be problematic if you assume the events are independent when they're not. So for example, if you are looking at or trying to gauge the probability of rain today compared to the probability of rain tomorrow, you assume these events are independent when there's actually an underlying connection, a larger weather system. It's also problematic when you assume events are not independent when they are. For example, hot streaks in the American example, in the reading, it would be baseball. But for others, it would just be like, let's say I flipped a coin 10 times and I got 10 heads, and all of a sudden I decided to bet it all on heads again because I was assuming that I was on a hot streak, that I was going to get heads again. But because each of these flips are independent, the actual underlying probability of getting heads the next time is actually 0.5. It's not related to what I flipped in the past. Another thing we need to be aware of when we're using probabilities is that clusters do happen. Sometimes you can flip 10 heads in a row. In previous week, I talked about a gentleman who was hit by lightning 7 times. Some people have won the lottery more than once, and you can assume that there might be an underlying bias in the data just because these clusters do happen. However, with a large enough sample, billions of people over 20 years, clusters of people getting struck by lightning more than once are likely to happen just by the basics of probability. And so these things don't necessarily represent something else. It could just be because of the latent probabilities, just underlying unlikely things actually happen. The next thing to be aware of is there's often reversion to the mean. So for example, if someone's extraordinarily tall and they have children, the likelihood is that they're likely to be closer to the mean height. They're going to be shorter than their parents because there's a tendency to have repeated values kind of move towards the center instead of repeated outliers. So for doing well on an exam, if you did really poorly one time, if you take the test again, you're probably likely to do better because the average score, you're taking the test multiple times, you're just likely to get more towards the average the more you take a particular test, or that's reversion to the mean. And another important risk when trying to look at probabilities, we talked about ecological inference in a previous week, is moving from aggregate statistics to individual behavior. For example, profiling. The readings talked about that Tom Cruise movie with predicting crime before people have actually committed it. After 9/11, for example, profiling people who went through security lines, or looking at aggregate statistics on a particular behavior and then applying that to one particular individual. Another risk is just garbage in, garbage out, that probabilities don't understand or know the quality of the data that they're using. And so if you have messy, potentially biased, or incredibly noisy data, that's going to be reflected in the probabilities and the conclusions that you're likely to reach from them. Finally, there's just a huge number, the speed in which the field is moving. These analytical tools are moving faster than the vast majority of people who actually use them would know how to actually be able to apply them. Artificial intelligence, machine learning, Bayesian statistics, there's a lot of things that are being developed quite quickly. They're becoming more complicated, that have often not a clear description of the underlying probabilities associated with them, that can lead to not fully understanding what the assumptions are, and therefore the conclusions that you're reaching from them might be potentially biased. One thing that's really amazing when trying to understand probability relates to that reversion to the mean earlier. The central limit theorem. And this central limit theorem applies to a sample size that has to be larger than, say, 30. So a pack of cards, 52, this would apply. That the sample mean will be distributed roughly as a normal distribution around the population mean. So if you have, let's say you flip a coin 50 times, the sample mean will be distributed normally. So if you flip a coin 50 times, a whole bunch of times, the sample mean for those coin flips will be represented by a normal distribution, which you talked about in a previous week, around the population mean. So if you flip a coin, let's say 10,000 times, and you take different samples of those coin flips, 50 or 100, that sample mean should be around 0.5 because it's going to be and distributed around it in a roughly normal behavior, because sometimes those 50 will have slightly more heads or slightly more tails, but they'll cluster. That sample mean will be distributed as a normal distribution around the population mean, which will be 0.5 as well. And the sample standard deviation will equal the population standard deviation over the square root of the number of sample observations. You don't need to understand that formula per se. I put it in words, but just to say that the central limit theorem makes a connection less direct than the connection between the sample mean and the population mean. But the standard deviation is a linear transformation of the population standard deviation over the square root of the number of observations, because the larger the number of observations, the larger the denominator gets, and it makes sense because then the smaller the standard deviation, because you should have that sample getting closer to the population. So this is the standard normal distribution. It's clustering around 0, and you have plus and minus standard deviations on both sides. Showed the example with the height example in previous weeks. I think the standard normal distribution has a couple of important properties. It's basically the bell curve, right? But the standard normal has a couple of really important properties that are fundamental to understanding the hypothesis test statistics that we're going to be using in this class. So the standard normal distribution, it's symmetrical around the mean. Both sides, you can fold it in half, they would be the same. The mean, median, and mode are the same. So the median value, the value in the middle, is the same as the average value, which is the same as the most common value, are all the same. And the predictable area, the probabilities under the area under the curve, is within a specific distance of the mean, is predictable. So within plus and minus standard deviation, 68% of the observations would fall within one standard deviation, 95% within two, 99% within three. And so those are the links between those statistical tables that we've seen so far in this class. You know, the 1 star, 2 stars, or 3 stars. That's a function of whether observations of the sample mean are similar or far away from that central tendency. Skewedness and kurtosis are two other measures. We're not going to figure out how to calculate them, but they're just a measure for how skewed towards the lower end or the top end the frequency is. Like income and wealth, it had a skewness towards those kind of upper values. Kurtosis is just how steep that curve is, how close together that those two sides of the curve are. The standard deviation I mentioned also for this, the standard deviation of the sample mean is given by a sum of all the differences between a particular value of y, that particular outcome, minus the average value or the mean value of y squared over n minus 1. N is the sample size. So this is that kind of calculation given the sample mean and the standard deviation. Now, when we're looking and moving towards regression, or if you ever see regression outcomes, sometimes you see means and standard errors reported. And I just wanted to spend a bit of time linking the standard errors to standard deviations to make sure that you understand that one is a functional manipulation of the other. So standard errors, here it's rho for the sample mean, is a standard deviation, which I showed you in the previous slide, over the square root of n. And that allows us to calculate confidence intervals. So with regression, you get the mean and the standard error for that mean. And what that you can do is get confidence intervals. So for polling behavior, you have a mean popularity for a particular candidate, plus or minus 2 or 3%, right, given the sample size. And the reason that they can figure this out is because of the standard error equation and the standard normal distribution. And as I mentioned earlier, right, that one plus or minus 1 standard deviation is 68% of the data, 2 standard deviations is 95%, 3 standard deviations is 99.7%. So often that's kind of rolled to 90%. The important thing to note also is that when you're talking about normal distribution, there's no normative implication to this. It's not good or bad. It's just one. There's an infinite number of distributions that we could draw. This is just one that's handy because we understand these important properties that the where the mean is, where the standard deviations are, that we can use probabilities to assign statistical significance and confidence around particular values. So confidence intervals, I mentioned those. It's important to note before I do that is what we're talking about here with probabilities. The distribution of the sample values is just, so let's say I choose these different values here of the beads, right? That's just the sample values of the frequency distribution. Those do not have to be normal. The average values will be normal. The sampling distribution mean, the means of the distributions will be naturally distributed, even if the underlying frequency is not. So, for example, if you're looking at for income inequality, right? You see, or wealth. You see, wealth is skewed towards those upper levels, and so you'd have a mean value for wealth, and you have the median. So the underlying distribution is skewed. But if you repeatedly sample 1,000 Australians over and over and over again, let's say 10,000 times, the mean value of income for all those different samples of 1,000 Australian citizens will be normally distributed around a mean that will approximate the population mean for everybody within the country. And I think that's something that's really subtle and hard to wrap your head around, but it shows the usefulness of the standard normal distribution, that even if you have a variable that is heavily skewed, like income within a country, that if you take samples of people and you want to understand whether that mean value of the sample is different than the population at large, you have a whole bunch of different samples. The sample mean of all those different samples is going to approximate the normal mean if you have a large enough group because of the central limit theorem. And that distribution of those sample means for the incomes, right? For if it's, let's say the average value is 50,000, so you grab 1,000 people over and over and over again from the total number of 25 million Australians, the average sample mean income will be 50,000, and the distribution of those samples, sometimes you might get somebody that is a lower, particularly low income in your sample, or higher income, and so you might have a sample, a particular sample that has an average value that's slightly below or slightly above that population mean. But those distributions of that sample is going to be normally distributed. And I think that's important to note, that the reason why we can use a standard normal is because of that central limit property, that those repeated samples are going to have a distribution that is symmetrical and has those characteristics. So how do we calculate confidence intervals? For, let's say, for polling for popularity, that people's popularity is within a range that we can define ahead of time. That is defined by the lower bound and the upper bound, which is given by the mean and the standard errors, which we showed earlier. So you have the lower bound is the mean minus 2 standard deviations if you're looking at a 95% confidence interval. And then the upper bound is the mean plus 2 standard deviations. So you have the mean in the middle, and then you have those standard deviations there. An example of this and the equation there that I showed you earlier calculates that. And it's interesting to think about how these confidence intervals are affected by sample size. So you think about what would happen if the confidence interval was if the sample was cut in half. So instead of sampling 100 people to look at their incomes, you only sample 50. Well, if you look at the denominator there, that you see the square root of 100 people, which is 10, is bigger than the square root of 50 people, which is a little over 7. So the confidence, because that's in the denominator, as the denominator gets bigger, the confidence interval gets smaller. So as the confidence the sample size gets smaller, the confidence interval is going to get bigger. So that's why we want to have as large of a sample as possible, because that increases the likelihood of that confidence interval being smaller. From a recent article, I mentioned this one in the previous weeks, I ran a regression model, which is something we're going to show you in a second, for a whole bunch of different variables looking at election integrity, perceptions of election integrity over a whole bunch of different variables. And you can see each one of those squares is the coefficient, or the estimate of that mean relationship between the x and the y. And the confidence intervals there are those lines that extend in both directions. And if those lines don't cross 0, then I reject the null, that there's no relationship between these two variables, in preference to there is a statistically significant relationship between these two things. For example, when election officials are fair, there's a positive value for the coefficient, and the confidence intervals don't cross zero. So that gives us an indication of the likelihood that this relationship is because of chance or whether it's tapping into something fundamental in the data that we're looking at. So we're looking at probabilities, we're looking at central tendencies. Those outlier cases don't often happen, but they do. We call them black swans. And quote from the reading, probability doesn't make mistakes. People using probability makes mistakes. And often when we look at probabilities, especially those tails after 3 standard deviations, those things rarely happen, but they can happen. And if you make decisions that can be quite costly if they don't, then you need to look at the expected value of those specific values, or the likelihood or the costs of those things actually cropping up in your variables that you're looking at. For me, this example, once I finish the lectures, I can finally get to the end of Squid Game. I did not watch it during lockdown. I'm making my way through it. But it is one of those, like with games, playing cards, flipping dice, or rolling dice, or flipping a coin. Often games have a clear and defined set of probabilities associated to them. So I thought, okay, can I try to apply probabilities to try to understand the expected value for a specific outcome? Often this is related to economics and dollar values for a specific outcome, or lotteries, for example. But for the Squid Game prize, I don't want to give anything away, but the Squid Game prize is, I think it's 460 billion won, which equals to about 49 million Australian dollars. That's the expected prize. The probability, the expected value is something different. That is the prize times the probability of winning. So you have that prize times the probability of winning, which is 1 out of 456 players, equals an expected value of $107,862, which is substantially less than the $45 million. And you also have to think about what the other potential costs involved with engaging in a particular activity is, especially with this kind of example. But this is just one kind of example in which you can try to use those probabilities, and knowing the probabilities as well as the value for the specific outcome in this dollar value that can give you an expected value for these for a specific outcome in particular. So a couple of quick takeaways for this brief overview of the basics of probability theory. First, probability involves uncertainty. We don't, social science, we're not sure because of the number of people, the number of different factors that can be shaping our actions, what is likely, what is going to happen, but we have some indication of what might happen, what the different options are for happening. So we have to try to estimate our uncertainty. Because we have only a sample of observations. We don't have the entire population of observations that we're going to look at. So we have to use sample data. Probabilities help us kind of quantify the uncertainties related to it. There are important assumptions, strengths, and weaknesses with the probabilities. And it's relevant to us in this class for what the research that we're doing in our ability to try to assign statistical significance to descriptive or inferential statistics. And again, there's choices that we need to make in how we define statistical significance. Do we want to look at 95% likelihood that the mean is going to be within plus or minus 2 standard deviations, 99% with 3 standard deviations? What is our level of uncertainty? There's rules of thumb of 95% is the most often used, but that isn't necessarily the only choice that we can make. So now let's turn to why we might conduct hypothesis testing and the different options, some of which we've already seen.